books in the back of the room in November. She read books, but she was super bright, very witty, really funny. And I was like, are you really this? Are you done in November? She's like, I'm done. And she started reading books. She passed the AP test. I guess there was enough that filtered in. It was that the family was really bright. Her brother made a 5 on the BC test and never did a homework the entire year. Not one. Made a 5. He just was really, they're both really bright. Anyway, so you guys I haven't had anybody who's completely checked out. I don't think. Maybe you have and you're faking it. But most people who fail this are the people that check out. And it's just too late to try to get back at the last month or something. Guys, we started talking about accumulation, right? So real quickly, without a ton of explanation, if you are accumulating from a smaller to a bigger number, smaller on the bottom, bigger on the top, that means you're moving from left to right. Because the starting place is the bottom number. That's the starting X value. The ending's the top number. If you're moving from left to right, any accumulated area or any area on the top is positive. Any area on the bottom is negative. But if I reverse direction, like if I'm going from, say, +3 to -1, that means I'm heading this way. Now any area on the top is negative. Any area on the bottom is positive. And what I didn't mention was, if you ever see a situation like, hey, I'm going from -6 to -3, which is to the right, and then this one says, hey, I'm going from -3 to -6, which is to the left, their answers are just going to be what? Opposites. So if you ever get a situation where you don't like going from right to left, and I know people over the past have like, oh, I hate going from right to left because then I got to remember that the top is negative. Well, then all you have to do is reverse the numbers. So like right here, let's just say I'm going from -3, which is right here, to -6. All you would have to do right there is go, well, all I really have to do is flip these numbers from -6 to -3, just put a negative on the outside. Now I can go from -6 to -3. This gives me a negative area. I negate the negative area and it's positive. So you have that right to do that. Or even better, what if I said, hey, the area from -6 to -3 is, and I'm making this up, is 10. Then what do you automatically know about the area from -3 to -6? It's -10, right? And then this is something I haven't mentioned. What would the area be from like 2 to 2? 0, because I'm not accumulating anything, right? So if you go from a number to itself, it's always 0. Every year I give some question, and I have this thing, and I have the integral, and I have this big function in there. And I see, and it's awful to integrate. Terrible U substitution. Really got to know your rules. And I see people trying to integrate this thing, but it's going from like 1,000 to 1,000. Sometimes I literally have seen people integrate it correctly, and then they plug 1,000 in. Well, you don't know, you do, but you don't know fundamental theorem yet. But they actually apply the fundamental theorem, and they plug the top number in, they plug the bottom number, and then they subtract and they're like 0. If it's the same number, it's always what? 0. Okay, so remember that ahead of time, and you're going to be in good shape. And then one more thing. When you integrate a rate, what are you going to get? I said this yesterday. I'm going to keep repeating it. A change in, not necessarily position. A rate doesn't have to be velocity. If it was velocity, it would be a change in your position. But a rate could be gallons. The reason why when you integrate a velocity, you get a change in the position is because what's velocity measured in? Meters per second, miles per hour. It's a distance, right? So you're getting a change in your distance or your position. But if it's gallons per minute, you're getting a change in the gallons, right? If it's snowfall per hour, you're getting a change in the snow, right? So you're getting rid of the like per hour, per second. You're getting rid of one of those denominator units, and it's going from a rate to a change in the amount, whatever that amount's talking about in your rate. So whatever the numerator kind of is in your rate, that's kind of what you end up with. If it was like meters per second, you end up with change in meters. Gallons per hour, change in gallons. Is that making sense? Get that beat in your head, and you're going to be in such great shape. Because there's so many times where they give you a function, and you're like, this function is gallons per hour, but they're asking me for gallons. oh, wait, if I integrate at gallons per hour, I'm going to get the change in the gallons. And it just kind of will come to you and make these word problems a lot more simple once you get that down. And we'll do that all this chapter, all the next chapter. We're going to keep doing that. And then we'll review the crud out of the AP test from March to when we take it in May. All right, did we get through all of these right here? Okay. All right, so let's just look at these. Right here, I've got this random function they're calling f of x. And then I'm integrating this function. And we know that not only when you integrate something, you get a change in whatever, but this is a function. So when I integrate it, integration means the area between the curve and the x-axis, right? So this is saying, hey, what's the area between the curve and the x-axis as I move from 2 to 5? So I am looking for, from 2 to 5, I'm looking for this area. And because I'm looking for just that area, and I'm moving to the right, that would be a what kind of area? Positive. So let's find the area of that. So what do you see here? And by the way, AP would have written this and they would have said, hey, the following function is composed of 9 line segments and 1 semicircle. They would say something like that. And you'd go, oh, yeah, it's not an ellipse. It's a semicircle. So the radius is 2. So can you tell me what the area of that is?
1/4 of the circle.
So it's 1/4 of what circle? Pi 2 squared. So it's 1/4 of 4 pi. So it's pi. So the area of that part is a pi. And the area of this is what? Well, it's a triangle. So 1/2 base times height. So 1/2. So that accumulated area is pi plus 1/2. And don't give me a decimal. I mean, I realize that 3.14 blah, blah, blah plus 5 is 0.814 blah, blah, blah. Just write it exactly. Now, the next one says, hey, what's the area from -3, which starts right here, to +7? And again, I'm going all the way to the right. I'm heading to the right. So I'm going to accumulate the area between this curve and the x-axis, between this curve and the x-axis, between this curve and the x-axis. But I'm going to keep going all the way to 7. And by the way, if you're ever wondering, on a semicircle, they will always go to the 3, to the 5, to the 7. They'll never go to the 6 because how do you find that part of a circle? You would need to actually find the circle equation or the semicircle equation. They're not going to ask you to do that. So they either have you go to there, to the middle, to the end, but not any other place. So how do I find this area? Well, what is that? Okay, you can totally do it with the trapezoid. Sometimes I look for little shortcuts. Like for me, and a trapezoid is fine. For me, I go, well, that's a square of 1. That's a square of 1. That's a square of 1. And this is what? 2 halves. So 1, 2, 3, 4. To me, it might be easier sometimes to do that. But or you could go, wait, this is a triangle. 1/2 times base times, that's a 2, times height. And this is clearly 2. So this gives me 2 plus 2 is 4. I don't care, or like you said, a trapezoid. I don't care what you do, but count it correctly because, again, on these problems, you're only getting credit for an answer probably. So this whole part right here is a +4. What is this part? Or tell me what you're thinking when I look at this. This cancels out with that, which is great because if one's negative and one's positive, they cancel. What's the point of trying to find those areas? But if I did want to find them, 1/2 base times height, right? So this one right here, if I did 1/2 times the base, which is 1.5, times the height, which is 1, you can see right here, I'd get 3/4, right? Is that right? 1/2 times the base, which looks like 1.5, times the height that looks like 1. So that would give me 3/4, but I would have to negate it. So if I had calculated, I would have gotten 3/4 there, 3/4 there. But again, they cancel, so I wouldn't even bother doing it.
My question is, how do you know that they can? You just kind of like assume.
Well, what is this slope? Rise 2, run 3. Isn't that rise 1, run 1.5? So it's literally right dead in the middle. So if that's dead in the middle, that's a 1.5, that's a 1, that's a 1.5, that's a 1. Right? I mean, I could get more technical and come up with an equation of a line and find the intersect, but I don't think I need to do that. Usually it's pretty obvious. But yeah, check it if you need to, because sometimes it looks like it's one thing, but if you actually check the slope, it wouldn't be. So, and then you already told me that this was 1/2 right there, right? And if that's pi, what's the whole thing? So this is half of a 4 pi, so 2 pi. So when you add all this together, you get a 4½ plus 2 pi. So 4.5 plus 2 pi if you want, or 9/2. What about -6 to 2? I'm going to get rid of all this. Let's get cluttered. What about from -6, which is right here, to +2, which is right there? Well, what's this area? How would you do it?
Triangle and a square.
Triangle and a square. Now I'm going to show you a number of ways. One, triangle, or triangle and a rectangle, or triangle and 3 squares. So that clearly is 3. And this is, and then you can say plus 1/2, base is 3, height is 1. So 3 and 3/2, so 4.5, that's 9/2, or 4.5. How about this? Isn't this right here half of that? So if that's 2, then this is 1. Isn't this half of that? So that's a 1/2, and this is 1, 2, 3, so 4.5. I mean, there are other ways you can do it if you're just kind of clever to keep from having to pull out trapezoids and triangles, but you can always do trapezoids, triangles, circles, squares, rectangles, whatever. But it's below, right? So if I'm going from -6 to 2, that's a -9/2. What did you say this was? +4. What did you say about these two things? So you end up with a -4.5 and a +4, -1/2. Right? -1/2 because it's below, +4 because it's above, -4.5, +4, -1/2. All right, just look at number 4. Number 4 is going from 3, which is right here, to -1, which is right here. I'm going that way. So what does that make this area up top? Negative. What does it make this down below? But again, don't these two things right here cancel? So if those cancel, I just have this what? -1/2 because it's going the other way. So it's a -1/2. Now, if you're like, I would have forgot that negative. Well, then do this. Put a negative there and change that from -1 to 3. From -1 to 3, you have a +1/2. So you carry the negative over to the +1/2, and it makes it -1/2. Either way, I don't care. All right? I'll do one more. Look at 6. From -1 to, actually, I'm going to do 5. From 2 to -3. So from 2 to -3 here is going from right there to there. So I want all of this area. Right? Now, once again, if I was going from 2 to -3, this would be negative, and this would be positive, and this would be negative, right? But those cancel, so I'm left with just that, and we already calculated that to be +4. So if you tack a negative on it, now we know that it is -4. Right? And then whatever you get, again, just to point this out, whatever you get for 7, that first part, you're going to get the negative version of it, or the opposite version of it for the other part. And then sometimes you'll see a thing like this. A lot of times you see stuff like this. Now, I want you to understand this function. This is saying that big G of x is equal to that. Okay? Now, we're going to talk a little bit more about the fundamental theorem of calculus later. But if I were to see this normally, hold on. If I saw that expression right here and it didn't have this, I would say, okay, this is equal to some new function, g, at x minus some new function, g, at -2. And that's called the fundamental theorem. Okay? That's what I would normally do. But because they said that this is just equal to g of x, then the only thing I can do is kind of assume that maybe this g of -2 did not have any value, and that maybe it didn't mean anything. So I'm going to do what they tell me to do in this situation. So I have this here because we technically haven't learned the fundamental theorem. All right, we'll talk about that later. So right now, all you can do is say, okay, if I want to find something like big G of 5, big G of 5 is what I get when I go from -2 to big of 5 on this function. Now, I didn't give you a graph, did I? Right? But let's just see if we can do this math. This is saying these are your x values. I want your big G of those x values. So this right here is asking me, right, for this box, can you find big G of -7? Well, what would big G of -7 be? It would be the integral from -2 to -7 of what? G of t dt. Well, here is our G function. So I'm going from -2 to -7. Here is my -2. Here is my -7. So I'm going that way, aren't I? So that makes any area above that now negative. So what is this area right here? And we've already done this. It's 1/4 of a circle whose radius is 2. And you know if a circle has a radius of 2, the circle would have a 4 pi area. You want 1/4 of that, so pi. But it's negative. So far I get a negative pi. But you also want this, right? Which is 1/2, base is 3, height is 3. So 9/2 or 4.5. But it's also negative, so negative 9/2. So based on the math I know, G of -7 right here would be negative pi minus 9/2. Now, what would G of -4 be? Well, G of -4, think about it, you're just putting your x right there. That makes this obviously not -7 anymore. It's -4. And -4, if I'm going from just here to there, -2 to -4, then I need to leave off all of this stuff, right? So what does that become? Just negative pi, right? Negative pi goes right there. And ask questions if you're not seeing this. Now, at -2, right here, if I make that a -2, what did we already know about when those numbers match? It's 0. And sure enough, -2 to itself, there's no accumulated area because there's no movement. That's 0. And if you recall what I said about the fundamental theorem, I said what that probably means is that G of -2 was 0, and that's why it's not showing up in this expression. And sure enough, G of -2 was 0. So that kind of confirms what I might have thought. But again, you don't know what the fundamental theorem is. It's coming. Now, what happens when I shift to G of 0? Okay, so now G at 0, I'm going from -2 to 0. I'm going that way. So now that area right here is, again, pi, just like the other area, but it's on the top and I'm going to the right. So now that's a positive pi. And what does G of 2 do to this? G of 2 extends to there. Now this part's tricky. That's the area at 2. What is the height of that? I gotta find it. Now guys, you didn't spend a year in geometry just for fun. Half of geometry was about proportions. You did proportions all the time, right? And here's a perfect example of this in practice. You know that that triangle is similar to that triangle. So if I want to know that height, I can say, well, the big one had a big length of 3, small length of 1. The small one has a big length of 2, small length of x. And you can solve for x and find that height.
Wait, if you just found that, you see those 3 whole squares?
Sorry?
The 3 whole squares at -1, you could just take half of them. So it's 3 halves.
It's not, it's 2/3, X is. You're just talking about finding the area. It's the area is going to end up being, yeah, half of 4/3. Yeah. So if you can see that, but guys, don't assume Cedric did, not to pick on him, but Cedric did, I'm glad he said it. He did what probably half the people will do a lot of the time and look at a picture and just look at it and go, oh, yeah, it looks like about a half. Don't make those assumptions. Use the geometry that you know. It is very common to do that. Very, very common. Look at it. It does kind of look like, oh, yeah, I'm down here. I'm probably about halfway. You can't about halfway it. And it'll look about halfway a lot. Okay? No, I didn't. I looked at the slopes. I looked at it and said, if this is rising 2 and running 3, then I am rising 1 and running 1.5. And then the next one would be rising 1 and running 1.5. So, and rise over run is checking sides of a triangle. So I was actually not eyeballing it. I was looking at it and going, based on this slope, it would have to cross in the middle. So I knew that those two lengths were at 1.5. I knew they were the same. And I'm going to do right here, I'm going to go, okay, let's just see. If 3 over 1 equals 2 over x, let's solve for that x by cross multiplying and dividing and go, oh, look at that. That wasn't half. That was 2/3. So the area there is going to be from -2 over, it's going to be a positive pi, but then it's going to be minus a 1/2 times the base 2 times the length 2/3. And you can see right there that that does give me a -2/3. So pi minus a 2/3. So yeah, Salem, if you can see a proportion and do it like that, awesome. But be careful on that stuff. And then if I'm going to 4, which is over here, to me, that one's a little bit easier, right? Because now I just have a 1/2. I can forget about all of this stuff. If I'm just going to 4, I still have this pi, and I know this next part's negative, but it's just 1/2 base times height. So that's clearly a pi minus 2. And then finally, if I extend it to 5, what happens? I'm just going to get an extra what? Plus a 1/2. So I basically have the same thing there, but I just add a little bit, an extra 1/2 to it, which would get me to pi minus 1.5. Or you could look at this and say, I mean, heck, there's so many ways. You could look at this and say, well, that negative part and that positive part canceled. So this just gives me that pi, and then base, 1/2 base times height, right there gives me 3/2. But it's negative, so pi minus 3/2. Y'all seeing these? So this is accumulation. It's not rocket science. It's just a couple of rules, but it's a very big part of AP Cal. And they will find clever ways to ask this question. And I will start with one. Actually, the skunk problem is a homework problem. I'm going to jump to some of, so is that. I'm going to jump to where we are today. So here's an example of how this accumulation might be thrown into a problem. This is not a great AP question, an AP style question, but it's a decent question to help you think. So here we go. 2 cars start from rest. So they're basically stopped, same place, and they take off at a traffic light, and they accelerate for several minutes. The figure below shows their velocities. Their velocities, okay, which is a what? Rate. So the question is, which car is ahead? Now, what do you know? How can you determine which car is ahead after 1 minute? You would need to know what? Their distance or their change in their position. And if velocities are always positive, the change in the position and the distance are the same. And your velocities are clearly always positive. Now, a lot of people make the mistake of doing this. They go, well, after 1 minute, they're kind of at the same place, which is kind of what they're supposed to look like. So they're at the same place. Wait a minute. No. After 1 minute, they're going the same speed, right? The same velocity. Clearly, this car on the bottom, which is car 2, was going much slower over that first minute, right? Than car 1 that was going much faster. Now imagine 2 cars right here. One of them is going slow, the other one starts going faster. But then right about the 1 minute mark, they end up going the same speed. So they're going the same speed at 1 minute, but clearly car 1 had gone faster most of the time, right? So he had gotten a lead. But what happens when I integrate a velocity? I get a change in the position, or basically how far I went. So it's not about where they're located at this point, it's about the areas below their curves. And if I look at car 1, this is car 1's area. That area represents the distance it traveled, right? This represents car 2's distance it traveled. That's its area. Which had the bigger area? Car 1 at this point had a bigger area, which meant it had a bigger change in position. And if it had a bigger change in position, it's ahead. Are y'all seeing that? So that's testing your knowledge of accumulation. Now, second question, which car is ahead after 2 minutes? Well, let's think about that. Here's 2 minutes. Which one has a bigger area at this point? Now, I would argue car 2, not because I counted, because I look at this and I went, somebody tell me this is really how you'll grasp it. What does this shaded region represent to you right there? The difference between them. So that would represent what? Car 2's. It would represent how far behind car 2 was or how far ahead car 1 was. Does that make sense? Now, what does this represent? Careful. Now, it does represent how much ground, how much further car 2 had gone than car 1 from that point to this point. But what does it mean if car 2 had gone that much more than car 1 in this interval, but that much less than car 1 in that interval? Overall, it went further, didn't it? Because all of this part's the same in here. So clearly I can look at this and go, oh, well, if car 2's distance amount area here is bigger than its area there, then car 2 is now in the lead after 2 minutes. Are you with me? But most people would get part B right because even if they're thinking poorly, they're like, oh, car 2's going faster here. True. But right here, look, what if I said, who's gone the furthest at 1 minute and 15 seconds? So right there, who's gone the furthest? And a lot of people go, oh, car 2's gone the furthest because it's higher. No, it just means at that moment, car 2 is faster, right? I mean, truly, if I give you a big head start and then I start running faster, I'm going faster than you, but I'm still behind you, right? The only time car 2 catches up to car 1 is when that area, whatever it is, matches this area here and he makes up for that loss. But at this point, has that area made up for that behindedness? Not yet. So car 1 is still in the lead here. Now, when does that happen? That'd be tough to calculate. And they wouldn't ask you a question that was unless they give you answers where 1 or 3 of them were totally wrong. Like they might go, is it at 1 minute and 15 seconds? Is it at 1 minute and 30 seconds? You might go, I don't know. I think that's still bigger. Is it 1 minute and 45 seconds? I don't know. You might have an argument that those are about the same. Well, they wouldn't ask you questions about 1:45. They'd ask you questions about 2 minutes maybe, or even 2.5 minutes, where that's clearly bigger than that. Does that make sense? But you still have to understand conceptually what's going on. All right, look down here. This one's a little trickier. This one says a car starts at noon and travels with this velocity. Okay, so here's noon. Time 0 represents noon. So noon is represented by t equals 0 on this function right here. T equals 0. So this is noon right there. All right, he starts traveling. So you can clearly see that and this is in hours. I don't know why it took him so long to accelerate, right? It took me 1 hour to get up to 54 miles a gallon. I don't know. Maybe he's like, did y'all even watch the Flintstones when you were a kid?
Yeah.
And you get in the car and they just paddle with your feet. I don't know, whatever. But for whatever reason, It's very slowly accelerating. So if this is velocity, what's the area under the velocity represent? My change in position. And if velocity is always positive, it represents distance traveled. So all this area represents the distance that the first car, or the car, right? The area represents the distance the car has traveled. Now, in a completely separated item, it says a truck starts at 1 at the same place. So a truck doesn't even go anywhere until here. But it starts moving and it travels at a constant velocity of 50. So here is the truck's velocity. All right? But it doesn't start until 1 o'clock. So here's the question. Approximately how far away is the car when the truck starts? So they're located at the same place. The car takes off at noon. So it's traveled for an hour. So how far away is the car when the truck starts? You don't have to actually figure the number out, but what would you be doing to find that? Whatever that area is, isn't that area how far the car has gone from 0 to 1? So whatever you got there, you count up those squares. I don't know. Now remember, be careful on the squares because each base represents what? What does each base square represent? A half, right? Because 2 squares is 1. So if I'm trying to find the area of 1 square, the base is a half, but what's the height of each square? 10. So each square represents 5 miles. I'm sorry?
Can't you just like factor it out and like re-multiply?
Factor what out?
The 5. Like, can't you just count up all the squares and then multiply?
Oh, of course. Yeah, that's what I do. But each square counts for 5. So if I was approximating, 1, 2, 3, I don't know, maybe this and this right here make up a 4. Maybe, 1, 2, 3, 4, 5, 6. You'd have to just kind of approximate. AP's not going to ask you to do that. They're a little bit more straightforward. But that area right there represents the lead that the car had, right? Second question. During the period when the car is ahead. So during the time when the car is ahead, approximately when is the distance between them the greatest? And when is the distance, and what is that greatest distance? So at what point do you think the car hits the maximum distance ahead?
I guess until they, what's the highest above the truck?
Did you say what you were going to say? I think you might be on the right track. What were you going to say?
I said like what the I guess where the car starts to slow it down and like the lines.
Where they meet. See, look at this. During this whole time, what could you say about the car's velocity? It's faster. So it's still getting further away, right? Faster. Still getting further away. Now, even though it's slowing down, it's still faster than the truck, right? Like maybe he's going 70-something here. He's going 60-something here. He's going 50-something here. The truck's only going 50. So it's still faster. But at this point right here, what happens? They're going the same speed. Now, the truck's way ahead, but now they're going 50. And then what? It's now going a little slower. Now, once it's going slower, what's the truck going to do? Start the process of catching up. So right here, that would represent, right there, it says, during the period, blah, blah, blah. It doesn't ask anything about what time. I would say at about 4.5 hours, the car has its greatest lead. What would that lead be? There's a couple ways you could do it. The lead would be what?
That's where the first part is, and then I guess the difference between what's above the red line.
So he's saying this plus this. That's the lead. That is the lead. Now, another way you could do it is just say, all right, I'm going to take the total distance the car went, which is that, right? And then I'm going to take the total distance the truck went. Now, remember, the truck started here. So the total distance the truck went is just that. And I could subtract those two, but what does that leave me with? That leaves me with just this pink part here and just that pink part here. And again, if each square is 5, you could go in there and count up the squares, approximate, multiply by 5. Are y'all tracking with me? So that's the lead that the car has over the truck. Yes.
Are you gonna ask us to approximate like that? On the
No. Yeah, I'll ask you to approximate, but it won't be like this where you're like, how do I figure out what that is? Is that like a 0.3? Is that a 0.6? Is that a point? No. And I don't think AP, that's why I said this is not a very AP-like question. Now, next thing. So it says, when is the distance? Oh, it did say when. When is the distance between them the greatest? At about 4.5 hours. What is that greatest distance? You would have to count up the squares to the best of your ability and multiply by 5. Last question. When does the truck overtake the car? Ooh. When does the truck overtake the car?
When the lead area is
When that lead area in the pink is suddenly matched by this, because this represents what that I'm coloring in? The truck is what? Is going faster, therefore is gaining up ground. So you would have to basically figure out what that number is and then slowly start the process of kind of figuring out what that is. It seems like it was somewhere right around in here. I don't remember what the key says, 7883, something like that. But at some point right in here, that area matched that area. But again, as long as you understand that concept, this is where the car gained ground. Here's where the truck gained ground. The break-even point, which would be when they catch up to each other, would be whenever that pink matched those two pinks. And if you get that, you're in good shape on this question. Right? Because rarely will they make you approximate with curves and stuff like that are kind of difficult. All right, this is going to be your first introduction to the fundamental theorem. Well, not really, because I mentioned it 2 seconds ago. The fundamental theorem of calculus, there's 2 of them. There's fundamental theorem number 1, fundamental theorem number 2. So the fundamental theorem says this, and there's 2 ways you can write it. Okay? Now, I'm going to see if you can make sense of this. What does A represent, assuming A is a time? It represents the what? The beginning and the start, or the starting time. What does B represent? The ending. And what did I say? We're going to pretend like this is a rate. What happens when I integrate a rate? I get a change in the amount. What that means is that these 2 things are amounts. This is the amount when? At the beginning. B would be the amount when? At the end. And doesn't it make sense that if this is a positive f of A, I could write negative big F of A here? What does it mean when you have an ending amount and a beginning amount and you subtract them? What is that? Change in the amount. When you integrate a rate, you get the difference from the beginning to the end, the change in the amount, right? Like if this said, hey, I ended at 20 miles, I started at 5 miles, 20 minus 5 is 15, that's the change in the miles that I went. Are you seeing that? Now, the way they happen to write it here, and guys, believe me, you will get this by the end. This is not going to be a big deal for you. Doesn't this say this? The beginning amount, like say I'm standing at some distance or location, plus the change gives me the ending. I had 2 inches of snow on the ground. I accumulated 12 inches of snow. What do I have in the end? 14. I began with this amount. I changed this much. I ended with that. That's the fundamental theorem, and that kind of makes sense, doesn't it? So with that in mind, what if I told you this? What does this mean? Remember what little f, big F, whatever? Actually, forget that for a second. Let me ask you this question. I know this big F and little f might bother you for a moment, but what happens if I were to integrate a derivative? What should I get back to? The original f. I would write it like this if that was f prime. But when I write it with regular f, I got to go back to something, and I don't know what that is, so I just call it big F. But if it's f prime, when I integrate, I go back to regular f, which makes sense, right? Regular f, take the derivative, you get f prime. Integrate an f prime, you get back to f. So when I integrate an f prime, I'm going to get back to some beginning and ending f function. Well, this says you're starting, I mean, what did I give you here? What function is this? The derivative. So I'm using this equation now for this fundamental theorem. Because the function I have is f prime. So if I integrate f prime, I get f's. So basically what this is saying here is what if your f of 0 is 2? F of 0 is 2 is like saying, hey, at 0, the f function would have spit out 2. That sounds a whole lot like the beginning amount is 2. Are you with me? So right here, if my beginning amount is 2, let's think about this. I'm going to go from 2 to something of f prime of x dx. I'm going to add to it the initial amount, and I'm going to end with some ending amount. That kind of makes sense. So right here, if I told you the initial amount is 2, and I say, what is f of x? What I'm essentially asking you for, is this, to use this equation. So let's try it. What if my question is, find f of 1? So to find f of 1, I'd be plugging a 1 there and a 1 there. Can I find f of 1? Sure. F of 1 is that, which is already given to you. And from 0 to 1 on the integration, 0 to 1 integrating f prime is asking you to find what? The area. What is that area? What is it? Negative 1/2? So I get 2 plus negative 1/2, 3/2. All right, stay with me for one more minute. What if I said find f of 2, not negative 2, but f of 2? How do I find f of 2? What do I do? To find f of 2, I get my initial amount, f of 0, which I already know, and I add to it the change in the amount from 0 to 2, which is all that area. What is that total area? Negative 1/2. What's 2 minus 1/2? Let's try it again. If I want f of 3, stay with me. F of 3 is the initial amount plus the change in the amount from 0 to 3. From 0 to 3, what's the area? Negative 2.5. What's 2 minus 2.5? We'll pick up with that tomorrow. Y'all have a good one. No, you're not.